In this lesson, we're going to be talking about implicit differentiation. And implicit differentiation is when you're taking a derivative of something that you don't explicitly know. For example, for explicit, you could have a function like y equals x sine x. I think is the one that the Stewart calculus book uses. This one is explicitly defined. Y is this, x sine x, and it only depends on x. In an implicit problem, you've got, for example, x cubed plus y cubed equals 6xy. So it's not exactly clear what y is explicitly. In order, you could potentially solve for y in this, but rather than have to go through the annoying calculations of figuring out what y is, the utility of explicit differentiation is that we'll be able to find the rate of change of y with respect to x, aka the derivative, without ever having explicitly found y. This, by the way, is some dorky little curve, again, from the Stewart calculus book. It's the Folium of Descartes. It's something like that. But whatever the case is, this thing is implicitly defined for y, not explicit like the top equation. So we're going to start with an example of hopefully an equation that is well known to you. Think for a second about what that is. It is, of course, a circle with radius 5. When we take the derivative of this, we're going to do the derivative and not solve for y. If you think about solving for y here, it would be 25 minus x squared, and then you take the root of it. It's just, this is one that I guess you could go through the process by explicitly finding y, but I just want to use it as a useful example of how to find the derivative of y with respect to x without having isolated y. So what we're going to do is we're going to pretend that this is x squared plus something we don't know squared. Because y is something we can't explicitly name, or at least haven't explicitly named in this problem. We haven't taken the derivative yet. Now, when we take the derivative of this, we'll do the derivative of x squared with respect to x. And it's important that I say with respect to x. Derivative of x squared with respect to x is 2x. The derivative of something we don't know, some function of x that we don't know with respect to x, is 2 of those guys to the first times the derivative of whatever is inside. Okay? And remember, this was our y value. So how do we express the derivative of the y value with respect to x? Well, that's dy dx. And I made this equal to 0 because the derivative of 25 with respect to x is 0. And again, though, with respect to x there means how much does 25 change when x changes? Well, none. So I know I've written this in a little bit of a strange way, but whenever you're doing implicit differentiation, just pretend that the y value is something you really don't know, that you really can't explicitly name. So now we get 2x plus 2y dy dx equals 0. And our overall goal was to find dy dx in the first place. So all we got to do now is isolate that thing. So 2y dy dx is negative 2x. So dy dx is equal to, when you divide the 2y over, negative x over y. I'm just going to look in the camera and make sure you can see that. Great. Okay. So that's actually the derivative of y with respect to x. Now you might look at that and say, wow, I've never seen a derivative with a y involved in it. Well, so what? What you're going to have is if you pick up any point on that curve, for example, 3, 4 is a point on the circle. I know that because of a 3, 4, 5 triangle. If you take this is your x value and that's your y value, you'll get negative 3/4 So on our circle, 3, 4 is maybe here, and the slope of the tangent line will be negative 3/4. Okay, so let's move on to this function, x to the 4th plus y to the 4th equals 16. And what we're going to do is we're going to actually take the second derivative here. So one goal is to take two derivatives, and the other goal is to expose you to the notation. So the first thing is this is 4x cubed plus 4y cubed dy dx. Remember, y is an unknown thing, and then derivative of 16 is 0. So anyway, we'll solve for dy dx. I'm going to just negative 4, so negative x cubed over y cubed. So that's the derivative of y with respect to x. This thing, by the way, you can look in the Stewart calculus book to see what this looks like. It's sort of like a circle that just got swelled out into the quadrants. It's not circular, but you'll see what I mean when you look at the picture. Now, to find the second derivative, and by the way we write second derivative is, remember, that's derivative, right? So, write it like that. This is the second derivative of y with respect to x. So what we need to do is take this thing and take its derivative. By the way, there's no dy dx or anything here. This, if anything, if you wanted to write something in there, you could think of this as dx dx, right? Derivative of x with respect to x. And then, of course, that's 1. Okay, so now the derivative of y with respect to x, you may notice that we need to use a quotient rule. So we'll do low d high, which will be negative 3x squared, minus high d low will be 3y squared dy dx over low squared, which will be y to the 6th. So this is and if you're wondering how I got the left side, it's just the derivative. Just let me make this a little more clean. Derivative of this is that, just by definition. So now, let's see, negative 3x squared y cubed. That is going to be positive 3x cubed y squared. Now, this is the interesting part of this, is that's dy dx. We don't want to solve for dy dx. What we're trying to find is this. So actually, this dy dx is right there. So if we just substitute that in, negative x cubed y cubed over y cubed, then this whole thing now is the second derivative. You could clean this up, obviously, simplify some stuff. I'll leave that to you. Okay, I'm just going to check the time, and then we'll see about doing arc sine. Okay, so we have plenty of time to do that. Just again, to reiterate this whole process, first thing is we're using implicit differentiation. This would be an explicit one, so we wouldn't need implicit differentiation for this. This one we would solve implicitly because it's annoying to get y alone. This is a simple circle. We did implicit differentiation here. The derivative of x squared with respect to x is simply 2x, but for y squared, since y is some unknown function of x at that point, we do 2y dy dx, and then solve for dy dx. Then we did a second derivative here. So we found our first derivative, which was this, and then we did low d high minus high d low, all that's d low, over low, low. And then we realized that we don't want to have, like, our second derivative shouldn't say blah, 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 blah times first derivative. Just take that first derivative and substitute it in. And then you could do some more simplification here, like I said. Okay, so what we're going to do, actually, is use this implicit differentiation similarly to how we took our definition of e to the x, and we used that as kind of a tool to get into the derivative of a to the x in general, we're going to now use the implicit differentiation as a tool to pry our way into inverse trig functions. So we're going to think about the function y equals arc sine of x, also known, of course, as y equals sine inverse of x. IB more commonly uses this notation. This, by the way, this formula is in your formula packet for the HL formula packet. The derivative of this is in the formula packet. We're just going to establish it so that you see where it comes from. The three you'll be responsible for will be arc sine, arc cos, and arc tan, not the reciprocal ones. Okay, so the first thing is to find the derivative of arc sine. We're going to rephrase this as a sign question. So think about, what does this mean, arc sine of x? Right? It says, where is, this is a where is question. Arc sine saying, where is sine equal to this? And it's there. So this will say, sine of y equals x. And we could get into the whole domain restrictions here. For example, you should have negative pi over 2 to pi over 2. I'm just going to totally ignore the domain restrictions. You can read about it in any textbook. But okay, so sine y equals x. And now we'll begin differentiating implicitly. We obviously could get y alone. It's right there. But we don't want to deal with that because we don't know the derivative of arc sine. That's our problem. We do know the derivative of sine, though. So what we're going to do is take the derivative of each side. The derivative of the left side, think about y again as something we don't know. What's the derivative of sine of something I don't know? It's cosine of something I don't know, times dy dx. And the derivative of x is, of course, 1. So now we can isolate dy dx. It's 1 over cosine y. Okay, now cosine y, think about what cosine y is, right? We know that sine of y is x. So let's start from cos squared y plus sine squared y is equal to 1. This is just a simple Pythagorean identity. We know sine of y is x, so this is really x squared. So cos squared y plus x squared, again, sine of y is x by definition. So cos squared y equals 1 minus x squared. So cosine y equals 1 minus x squared. So dy dx is equal to 1 over root of 1 minus x squared. So that, and again, remember what y is arc sine. So if you wanted to think about it like this, d dx arc sine is 1 over 1 minus x squared. There are, of course, similar derivations for the arc tan or tan inverse and arc cos or cos inverse. So we've used implicit differentiation now as a tool to develop that. And of course, any function that we can throw up here, any polynomial function that has all kinds of mixes and matches of x's and y's and everything else, we can use implicit differentiation for without actually explicitly solving for y. So that's the lesson.